Fantastic. Kimberly, thank you so much for joining us. I'm super excited about this event. I can tell you that you have, it looks like, 2 formal methods people. You've got Sean, who does machine learning and maybe, unlike me, knows about ODEs, and Brennan, who does more practical computer science, and Jacob, who does more practical computer science. You have a diverse audience, and there's more people who watch afterward. We're very excited to have you. And with that, the floor is yours. So feel free to screen share or not, or whatever works for you.
Okay,
I'm excited about the event.
Yeah, so, okay, I apologize for my incredibly corny title. I didn't know, I was like, yeah, I apologize for that.
It's perfect.
So, like I was telling Max earlier, by the way, so I kept my prepared, my prepared slides here pretty short. And so, like, please, there's plenty of time for you to interrupt me. I'm also like, I wasn't totally sure what the audience was, and I am much more used to talking to mathematicians. So if there are any questions or anything that I don't define that you need me to define, like, please, just feel free to interrupt me. There's plenty of time. So, like, I'm hoping we can keep it, we're a small group here. We can keep it pretty casual. So feel free to just totally unmute yourself and just jump in if there's anything that you need clarification on. So yeah, and I actually was really excited when I actually kind of had a moment, and Max knows this, I had a moment as I was preparing this, that I realized that the term hybrid systems can mean like a variety of different things. And I was like, wait, they know like which type of hybrid system that I do, right? Like, then this is not like, because there was something like fuzzy logic and something, and I was like, that's okay, that's not what I do. And there's something in like mechanical engineering, and again, not what I do. So okay, so what when I say hybrid systems, what do I mean? Okay, so what is a hybrid system? So at its most basic, a hybrid system is something that exhibits both continuous and discrete behavior. So you as computer scientists are probably do much more, and I apologize if I'm wrong, you think much more, I think, in discrete terms, right? Like, I'm thinking every time I write code, like, everything's very discrete. Like, every time I do a for loop or something, right, that's a very discretized process. Whereas a hybrid system is something that combines some of that discrete behavior with a continuous component. And the very canonical example of a hybrid system that you see everybody talk about whenever you have an introduction to hybrid system is a bouncing ball. So if you imagine a ball that's bouncing, the idea is that when the ball is in the air, everything changes smoothly and continuously, right? There's an effect of gravity on the ball. And so that is like, slowing down the ball's velocity, but that's happening continuously and smoothly, right? There's no abrupt changes happening while the ball is in the air. But the instant the ball hits the ground, right, there's that instantaneous change in direction, right? And that comes from the ball. And physicists tell me that I'm oversimplifying. Whenever I do this, they always kind of like give me a look. But for now, we're just going to go with this model that every time a ball hits the ground, it instantaneously reverses direction. So there's that discrete component that's built in to a continuous system. And so if I were a mathematician, which I am, and I were trying to model a bouncing ball, one way that I could do it was, okay, let's let X be my variable that represents the ball's height, and Y is going to be the ball's velocity, and we know that velocity is the derivative of position or height, so Y will be X prime. And then I can write when X is greater than 0, so that means, again, when the ball is in the air, right, when its height is positive. Dx dt is Y, that's that same as Y equals X prime. Dy dt is negative G, and that is that negative, G here is going to be my gravity. So my acceleration due to gravity, because I'm on planet Earth. But when x is equal to 0, that's when we see that instantaneous change, right? So x will go back to x, the height doesn't change, the height is still, the ball doesn't kind of teleport, right? So the ball's position stays the same, but the ball's velocity changes, whereas y, whatever velocity it's approaching the ground with, it instantaneously reverses and goes in the opposite direction. And you can include, depending on your model, you can include a lambda there, which is some kind of, loss of capacity of the system, right? If there's, if you want to represent the ball, like eventually kind of loses height as it goes, maybe it loses some energy as it goes into the ground. So you could let lambda be some positive constant there just to kind of represent, or if you wanted to do kind of an infinite bouncing ball, you could let lambda be 1 there. All right, any questions so far?
Well, I don't mean to jump into something super technical. If
No, please do.
Okay.
Yeah.
So I'm more accustomed to like the automata theoretic presentation of a hybrid system where you have an automaton and then you have like some ODEs that are associated with each state. And then
Yes.
like your jump is based off conditions on the variables the ODEs range over.
Yes.
And this seems more like a piecewise, functional presentation. I don't know the right words, but like you have piecewise ODEs or something like that. So I guess I'm wondering, are these like equivalent notions?
Yeah, so the way, and I'll kind of, in my next example, you'll kind of see that as well. But the idea is that you are kind of like stitching together these different differential equations, like you have different systems and different differential equations that you kind of stitch together in like a discrete manner. Right. And so the way that stitching happened can be, like you said, like can be some sort of state dependent. Yeah. It's dependent on some kind of like external condition. Right. Right. I apologize. My dogs are being noisy behind me. Hilbert.
They're defending you from the computer scientists.
I know Hilbert's named after a mathematician, so he's
okay.
Like Hilbert. It's okay. So yeah, you'll kind of see that more in my next example. Okay, but yeah, great question. But you do kind of see again, like there's that condition aspect here that kind of tells you again, like looking to that other condition to say like what is going to happen with this change. Okay, so let's consider another example. So let's suppose I have, and again, I don't know if you have taken differential equations or if it's been a while since you've taken differential equations. So please, again, feel free if I need to explain things a little bit further. But let's consider 2 different differential equations on the unit interval 0, 1. So dy dt is x times x minus 1, or dy dt is negative x times x minus 1. So you can see already there's going to be some symmetry between these 2 systems, right? Hilbert. It's okay. I don't know what he's growling at. So like I said, these are kind of mirror images of each other, right? Because of that negative sign that's present or not present. Both of these have fixed points at the endpoint, so you can kind of consider just that interval by itself. You don't have to look. I like to study examples of differential equations or dynamical systems on what are called compact sets. So compact, broadly speaking, means like sets that don't kind of go off to infinity and that they're also like contain their boundary, right? So this set here is compact because it's kind of within a finite range here, and it contains its 2 boundary points, 0 and 1. So this is a compact set here, the interval 0, 1. I like looking at dynamical systems on compact sets because that guarantees that you have some kind of convergence at some point, like something has to kind of accumulate somewhere. If you don't have compactness, you're not guaranteed that. And so that's why I kind of am limiting myself here to just the unit interval 0, 1.
And that's because you don't contain your limit points necessarily. Is that why?
Correct. Yeah,
okay.
You don't necessarily contain limit points if your set's not compact, exactly. Or I could have systems. I could have equations that run off to infinity or negative infinity if my set were like unbounded. So I like looking at compact things because that kind of guarantees me limit behavior that is nice and easy to talk about. But that's just kind of like, that's what I study. There's certainly systems that are not on compact sets. So in this, and now I have to remember which one's which. If all my x values are in between 0 and 1, right? So if I plug in a number for x that's between 0 and 1, like if I plug in x equals 0.5, you'll notice x is going to be positive, but x minus 1 is negative. So I have positive times negative is a negative number. So my derivative is negative, which means that these functions are going to decrease, right? So if I start somewhere along the unit interval, eventually the idea is that we kind of move to the left and everything kind of converges at this fixed point of 0. Whereas with the other system, mirror image, the exact opposite thing happens, right? If I start anywhere along this line, I get convergence the other direction to 1. And so that's what happens in these two individual systems if I consider them separately by themselves. But what if I wanted to combine these two systems somehow? So what if I kind of wanted to alternate between these two systems? And as Max mentioned before, there can be conditions on like when, maybe there's some external condition that determines which of these two systems you are in at any given time, right? I tend to study systems that alternate or that switch sort of on a regular basis. So if you can imagine like switching between these two at regular time intervals, what's going to happen, right? If I start, maybe I start with the bottom system, which is where we go to the left. To the right. I'll go to the right for a while, and then that switch happens. So there's that instantaneous, that discrete change. And then we move to the left and then switch again, move to the right. And you can see what happens is that if that happens at regular time intervals, you're going to end up kind of suspended, right? On some sort of symmetric interval over here. So this presents a little bit of a challenge because what a lot of people in the past have done is they're like, oh, if we have two dynamical systems here, two differential equations on the same space, this 0-1 interval, and I were to consider combining them somehow. What we're going to say is that the combined system, we're just going to kind of average the limiting behavior. And so like this one has an attracting fixed point at 0, the other one has an attracting fixed point at 1. We'll just say that the combined system would have an attracting fixed point at 0.5. And as you can see, that's a little bit too simplistic, right? Because 0.5 is not an attracting fixed point. It's not like everything kind of gathers in the middle. I mean, it could, depending on what your switching regimen was. But as I showed you, if we take a really pretty simple example of just switching at regular time intervals, you see this kind of like suspension in the middle, which is totally different from any behavior that you would see from any other, like any one differential equation on the system. So we have to make the problem a little bit harder for us to apply like our classical dynamics to the problem before we can kind of like, apply a lot of the definitions and theorems and things that we're used to talking about. So, okay, so this was my example of like what's going to happen, right? If you kind of alternated at regular time intervals. So here we're just like at integer times are switching, and you can see again that kind of like piecewise behavior. And here at those start corners, that's where you see that discrete change happening. Okay. So like I said, and this behavior, you're not going to see you're not going to see this type of a behavior there's no differential equation that I could write on the unit interval 0, 1 that is going to give you this behavior. There's like, I could not write one differential equation that gives you that. And I guess maybe I can try to open up to some audience participation if people are up for it. Does anyone see any reasons why that might be? And again, I know it's probably been a while since you've had thought about any differential equations. Matt.
I'm just going to take a guess here, but
yeah, totally.
It seems like each of the equations only depended on your position, your x, but now you have this sort of time dependence of some sort.
Exactly, right. And I guess I should say, like, you're not going to see an autonomous system, that one that doesn't have a time dependence, because you can see, for instance, okay, let's consider like the point 8. When you visit point 8, your behavior is different depending on which system you're in, right? Here, if I'm at point 8, I'm going through it from directions from right to left. But here, when I visit point 8, I'm going from left to right. I might have switched the directions there wrong, but you get the idea. The direction I'm going is sort of dependent on my time, right? And so I can't write like one autonomous, nice differential equation that's going to encompass all of that behavior, because there is that dependence there, that where I see different behavior depending on like what's going on, what system is kind of in charge at any given moment. Okay. So how do I model a hybrid system? I'm going to borrow an idea from control theory. And one thing that this does kind of, and again, as mathematicians, we take everything and we make it very theoretical. One thing this does require us to know is that we kind of know ahead of time what the pattern of switching is going to be. So like Max said, it's possible, depending on if I had some kind of maybe, and this is another thing that I do look at as well, if I implement some kind of maybe an element of stochasticity or randomness to my system. But the idea is that, like, if I'm sitting here right now and I want to write a model, I'm going to kind of know ahead of time, like, what the switching pattern is going to be. So the pattern of like how the switches are going to happen, at what time points those switches happen, am I switching from system A to B to C, or am I switching from A to C to B? You know, how does the switching happen? I kind of know that ahead of time. And so what I'm going to do is I'm going to have a totally separate, I'm going to consider that switching behavior kind of separately. And the way I'm going to do it is I'm going to write this function U of t to be that piecewise constant function, which represents the discrete changes in the system. So you can imagine, for instance, if I, maybe I label these two different systems here, let's call them A and B, right? If I wanted to talk about the switching behavior, and if I were switching at regular, let's say I switch at every integer time unit, I would just have a piecewise function that's like A from 0 to 1, and then B from 1 to 2, and then A from 2 to 3, and then B from 3 to 4, and so on and so forth, right? So I kind of have mapped out all of the switching that's going to happen ahead of time. So those jumps there, right, between when I switch from A to B, or however I've kind of notated the different systems that I'm working with, those represent those discrete changes in the system. And here I get a little bit into the weeds. But what I want is I want to be able to talk about that switching behavior as a dynamical system in and of itself. So apart from like what's happening with, you know, the differential equation, for instance, on the unit interval, just looking at the switching, just at the pattern of the switching, I want to be able to talk about like how that thing is changing over time. And so the way that I'm going to do it is I'm going to take that piecewise constant function, and I'm basically going to imagine, you might remember, and again, it might have been a while, talking about like horizontal translations of functions, right? So basically I grab the function and I kind of like drag it horizontally around. So basically what I'm gonna do is I'm gonna grab that function. I'm just gonna kind of drag it all the way around, and I'm gonna consider all possible different horizontal shifts of that function. So that is all of those things together are gonna be, I'm gonna put them together in a set called lambda. So those are all of those shifted functions. And the way that I kind of transition between them is through the shift map. So you can imagine, you know, this function is basically just shifting it's kind of like, it's like on a little conveyor belt, and it's just kind of like shifting continuously to the left. And that is its own like dynamical system, really. So that's what I'm doing here. So again, this is totally independent of what's happening, again, on my unit interval or whatever space, you know, subset of the real numbers that I'm looking at. This is just the switching behavior by itself. And again, I'm getting pretty theoretical here, but like, if I want to talk about dynamics, especially if I want to talk about things like limit behavior, if I want to talk about like how close two things are or far apart from each other, we need a topology on this, right? Like, I need some kind of a structure for this space. Like if I were to, you know, if I take the letters of the alphabet, like A, B, C, D, E, F, G, etc. Like there isn't, I guess there is kind of like an induced topology on that, but like it doesn't really, like I don't have kind of a set, like an idea of like where those things are relative in space to each other, right? Or if I took maybe the set of people that was like all 8 of us and put us all together in a set, there's no, like we're just a collection of people, right? There's no relationship between like distance or how far apart or how close things are. And so I need some kind of a way of measuring that. And right now, all I have is all of these functions together in a set, and I don't really have a way of talking about like how close or far apart two functions are. So I'm going to define a metric, a way of measuring a distance between these two functions.
By the way, Kimberly, just so you feel safe, everybody here should know basic real analysis. And
okay, good. So yes, so we should have some basic real analysis. So yeah, so I need to have a metric space. How about topology? How are we feeling about? I guess we don't really need topology.
Probably basic point set, I think, is fine. But if anybody has a question about a definition, they can speak.
Okay. But, well, so I mean, I need to induce a topology on this system, right? And I can do that by defining a metric. So, okay, so the way that I'm going to define this metric on this function space is I'm basically gonna like, for every kind of unit of time here that is like a unit long, I'm basically, if I have two functions, I'm just going to compare like how far are they, like where do they agree and where do they disagree? And I'm just going to kind of count up, I'm just going to kind of measure how long, like where do two functions kind of agree and overlap with each other and where do they disagree, right? So that's what I'm doing down here. And then once I've done that, I'm basically going to add up all of the like lengths on which they agree and disagree, but I'm going to weight it because I need this thing to converge, right? I have an infinite series. I'm going to weight it by 4 to the absolute value of I, so that guarantees that convergence there. And what that does is that kind of focuses the importance on parts of the functions that are closer to 0 and decreases the weight further out in the tails, right? So two functions are going to be closer together if they are more similar close to the origin, but maybe differ out in the tails, versus functions that are different really close to the origin, but maybe agree out in the tails. So there's that kind of like gives that focus there. And I really, the way I imagine is like the way I kind of think about it is like I'm kind of focusing on just like the origin, and things sort of get blurry like as they go further out. And then as these functions shift, different parts of them kind of come into view, right? If I'm focusing just on the origin and then I'm imagining this function shifting, like different parts of the function kind of come into view. So that is what's happening here. So now I have a metric space. I have an operation that gives me a dynamical system. So I can talk about dynamics on this metric space, and I can apply all sorts of different like classical dynamics results and definitions to this space. And I won't kind of get into what all of those are, but it does at least allow me to kind of talk about these things that we're used to talking about for dynamical systems in this space. And that refers to the switching behavior. So I've kind of taken the switching behavior and I've made it its own dynamical system, which is sort of cool. And then what I need to do is, so I have the kind of switching space, that function space, but that wasn't really the thing we were interested in, right? The thing we were really interested in was the behavior on like the unit interval 0, 1, or, you know, again, whatever metric space, whatever subset of Rn, for instance. It doesn't have to be a subset of Rn, but for simplicity, usually, whatever compact subset of Rn, I was kind of like focusing on with my differential equations at the beginning, right? So what I'm going to do is I'm going to have those two guys kind of run simultaneously to each other. So the function space is running in the background, and then what's happening in the foreground, kind of in that like subset of Rn, is it's getting information from the function space that tells it like what system it's in at any given time. Right, so it's going to look to the function space, and the function space is going to kind of update and give it new information and be like, okay, right now we're in system A, we're in system A. Okay, now you got to switch. Now you got to switch. Now we're in system B. Now we're in system B. Okay, switch. Now we're in system C. You know, whatever that switching is, and so that's all this and that kind of thing where I consider those two things running parallel to each other. The fancy name for that is the skew product flow, and that's kind of all that I'm saying here is I've got these two systems that kind of run parallel to each other. But one system is kind of independent, does its own thing. The other system is looking back at that first system to get information and update. So delta was, again, that function space from before, and that does its own thing, right? That's just the switching. It doesn't need any additional information. It just kind of runs and does its thing. M here is going to be what happens kind of in the real world. But M kind of is always looking back to delta for information. So the analogy that I gave my students was like, let's suppose, and I'm not in politics also, this might be a really bad analogy, but I'm imagining, like, let's imagine there's some kind of like the president or something is giving a speech, but he's giving a speech about some event that's like kind of happening in real time, right? So he's like trying to update the public, and he's getting information like through an earpiece from his like aides or whatever in the background, who are going to inform him if the situation that he's talking about has changed somehow, right? But what we see is the president talking, like we, the public, see the president talking, but in the background, there's something that's going to kind of tell him if something switches. Right. So all we're observing is the president's behavior, but we know that in the background, there's something else happening and that he's getting information from somewhere else. And those other people are going to kind of update him if something changes, if something switches. So that's kind of what's happening with the skew product flow. I can't, in terms of dynamical systems, just consider like what the president is doing or what's happening in my subset of Rn on its own, because it doesn't follow the classical definition of a dynamical system. It kind of violates all of these axioms that we require. So I can't apply, for instance, things that I want to talk about like limit behavior or different definitions of recurrence. I can't apply those just in those systems, but when I consider the two running in parallel, then I can. So example, like, right, I can let phi here be the solution to this differential equation, and here is my kind of switching function happening, right? So there's that function happening in the background, but it's kind of updating what's happening here. So this differential equation is getting information from this switching function that tells it how it's going to switch. So that's just one example. And I kind of got ahead of myself a little bit. I sort of said all this stuff already, but I said the point in studying the skew product flow is because it takes the hybrid system, which is this kind of weird thing to kind of wrap your head around a little bit, and it changes it to a classic continuous dynamical system where the discrete component is sort of built in. So when I say continuous, rather what I mean is not necessarily continuous, like you might still see jumps or like sharp edges happening, but I mean continuous with respect to time, right? There's a time continuum there rather than like a, a discrete process that takes only integer times. I now have something that runs across like the whole real numbers. And I can apply all of these classical dynamics concepts to that product space, right? So I can talk about non-wandering sets, for instance, as a subset of the product space, right? Fixed points, but those are going to be fixed points that are a subset of a product space. Asymptotic stability, chain recurrence. And again, I'm not going to define these things because you don't really need to know them. If you're interested, I can tell you, but these are all going to be things that are happening as a subset of a product space, right? So every time I talk about a point, really, I mean an ordered pair of points, right? Something that's a function and then something in Rn. Those two things come together as a pair. And so one thing that I do is I'm like, okay, it's really great that we can study this all with and this is one thing that I did for my PhD work, is I was like, okay, it's really great that we can study this as a product, but like the Skew product was a little bit unwieldy, right? Everywhere I go, I have to look at pairs of things, right? I have to deal with things on a product space all the time. And really the only thing I care about, the thing that I want in the foreground is what's happening like in Rn. I don't really need the switching behavior in the background. So if I were to take projections from the product space and just project it down into the subset of real numbers, what do we lose? What do we gain? Do we retain, like we kind of have to adapt our definitions a little bit. Do we retain some of these kind of like recurrence concepts? So one thing that I did for my dissertation was I kind of made up new definitions for like, what does recurrence mean if I'm just in this isolated, if I'm looking just at Rn and not with its paired kind of function space in the background. So you have to redefine, for instance, chain recurrence is something that I looked at. You have to like come up with a new definition because the regular definition doesn't work, doesn't apply. And then I want to ask myself, like, is there a relationship between like what I think of chain recurrence in just like the subset Rn versus chain recurrence on the entire product space? Like, is there a relationship there? So that is work that I did as part of my PhD. I haven't thought about that stuff so much recently, mostly because I came across a really hard problem in the process. And after talking with a couple of dynamicists, they were basically like, oh, that's really hard. Like, I don't know if we're going to get that. And so I kind of gave up on that problem for a while. And now one thing that I do is I look at stochastic perturbations to dynamical systems. So this process that I did here requires that we kind of know in advance everything that's going to happen, right? And everything's going to happen like with probability 1 or 0, I guess, how the switching is going to happen. But what if I don't know ahead of time how the switching works, right? What if I modeled that with some kind of a discrete stochastic process, like a Markov process, or a Markov chain rather. A Markov process is more continuous. Things get really weird when you do that. For instance, if I have a chaotic system, by perturbing some element of stochasticity, you can actually stabilize chaotic systems. And the example for that is, or I guess unstable systems, you can kind of stabilize. And one example I have for that is, has anyone ever tried to balance like a meter stick in their hand? Right? Like balance it upright. I always did this as a kid, right? And it's like really hard to get the meter stick. Like if you're holding your hand still, it's really hard to get the meter stick perfectly balanced, right? So that's an unstable system. But if you kind of like, if you move your hand around, that helps, right? If I kind of like jiggle my hand a little bit, that actually helps you kind of balance that meter stick upright. And so that's where we see that addition of like that noise there into that system actually helps you stabilize something that was previously unstable. So that's stuff that I'm doing now. And I guess I'll kind of like leave it there and open it up for questions.
That was awesome. Thank you very much, Kimberly. I think I'll start and then other people should jump in. So can you explain, I know there's like funny business with Zeno's paradox in hybrid systems, but I don't really know how this works in your presentation, but, or another way to put it would be like race conditions between the discrete stuff and the continuous stuff.
Yeah. Okay. Yeah, you can definitely. So this is where it's nice to kind of know ahead of time everything that's going to happen, right? If I kind of map out all the switching ahead of time, because you're right, there could be conditions where like if switching's happening like too quickly, right? You could end up with things kind of converging in finite time, which you don't really want them to do, right? Or you could end up like with the Zeno's paradox stuff, like you could end up with a system that can never really like catch up to itself, if that makes sense. So that gets a little bit more into kind of the conditional switching stuff, which I don't know as much about because I'm like, as a theorist, I'm like, let's just assume that we know everything ahead of time and I can like put it down on paper and map it out, which is really convenient to do when I'm studying it from the standpoint of theory, right? But like from application, if I were to write some kind of code that was giving me some kind of conditions on the switching, I would need to make sure, like I'd want to make sure that I avoid those kind of situations, right? And so, yeah, unfortunately, I don't have a super good answer for you because my answer for you is like, let's just assume that doesn't happen. So that's the kind of thing where like, but yeah, there are definitely things like that that you need to kind of like make sure that you're trying to avoid. And that's why you know, you do want to be pretty careful about the like conditions of your switching, right? And oftentimes this is why I say like, you don't like, you want to be careful, and I'm sure as computer scientists, you know this, you basically want to be careful that things aren't getting too like self-referential, right? Like you want to have a kind of nice chain of command for how things are, for what the order of like how, what's dependent on what, right? So for instance, right now my switching behavior, the way I have it written is like totally independent of anything else, right? It doesn't have any dependency on anything. And so it kind of is able to do its own thing without dependence from anything else. If somehow the switching behavior was conditional back on what was happening in the real world situation, then you can end up in these sort of like awkward self-referential loops, right? And I'm totally positing here about this, but I think you want to be kind of careful again about the sort of like chain of command. So I'm thinking like, you know, the president is giving his talk and his aides in the background are getting information, but if part of what the aides were gathering information was like, what was the president saying at a certain given time, right? If they were basing their information off of what he was saying, you can end up in this like really awful like feedback loop, right?
Yeah, that's exactly the sort of thing I was thinking of. Like in computer science, we'll build these models and then the model like can't progress past some time because of some self-reference like this.
Yeah, exactly. So I guess, again, my answer isn't super great. It's just basically like, don't do that. Okay, then Brendan is asking, yeah, so like I said, we are borrowing a lot from control theory here, right? So one thing that I did when I was doing my dissertation was my advisor had kind of written this book all about control theory. And I basically like took a lot, like I told you, I had to come up with my own definitions for things. I basically took a lot of his definitions from things that he'd come up with in the language of control theory and adapted them to the language of like hybrid systems. So there's definitely a commonality there. I guess the difference is really in between, like in control theory, the idea, like the word control is the idea that we have control over, you know, some parameter or something, right? Like that we are able to kind of toggle it at will. Whereas with hybrid systems, we don't necessarily have we kind of have to work with whatever has been handed to us, depending on the system. We don't have control over the switching. So, control theory leads you to things like optimal control, right? Like, how can I optimally switch things to get an optimal result? Whereas what I'm doing is like, we can't necessarily tease out that difference, right? We can't necessarily like tweak the switching. But like you're correct in that the two share a lot of commonality. So I do think that analyzing hybrid systems can be helpful for those who do control theory. Thank you, Jacob, for coming. I think it is a little bit more limiting, right? In that, like, you're often handed down the switching behavior kind of ahead of time and you can't really change it. But I think that working within that mindset might present some new challenges for control theorists. If you kind of were like, oh, well, maybe I'm more limited in like how am I switching, or how I'm able to control this system. But you're right, the two, and I think so. Oftentimes, the other thing with control theory is that like oftentimes your control is allowed to be like a continuous function, right? Whereas I was talking about in hybrid systems, I'm talking like a piecewise constant, which is going to have jumps and jump discontinuities. But one thing that we do see a lot, and I don't know how much optimal control anybody's done. Oftentimes when people do optimal control and try to find like an optimal control function for whatever system, those controls end up being what we call bang bang controls, which are exactly piecewise constant controls. Oftentimes we see that those bang bang solutions end up being exactly those piecewise constant ones that are going to end up being optimal. So like, I think, for instance, I studied at one point an optimal control model for looking at like a cancer model. So I have some kind of a model that represents a tumor and how the tumor grows or shrinks. And there's a parameter in there that represents kind of, some kind of treatment or medication that's given, and the dosage might change over time, right? And what the optimal control model told us was like the optimal model was actually a bang bang system. So it was basically like give all the dosage at once and then discretely stop, and then stop giving the dosage. Like that ended up being the optimal method. And so I think looking at the language of hybrid systems and looking at those kind of incorporating those discontinuities into the system, like we're already seeing that that is something that we need to study, because like I said, oftentimes those bang bang solutions end up being the ones that we see. So
I think that's also related to, I don't know the right term, but there's this problem in formal methods of like coming up with the guards for a hybrid system. So like you want your system to satisfy some property, and you don't know basically what, when you have a piecewise function, like what the conditions should be for the different pieces. So
sure,
you come up with the conditions, like the jump conditions basically. And
right.
So I think it would be like, I don't know, Daniel might know better than me, but like reactive hybrid controller synthesis or something like this. There's some term for that problem, which would also be kind of a control theoretic problem, but it's not exactly optimal control. It's something different.
Right. Yeah, I was actually really fascinated when you first reached out, because I'm a theorist, right? And so I didn't know. I mean, I could tell you, I was like, oh, hybrid systems, there's probably some application of those. And I was thinking kind of more in like maybe like biomedical sciences, where like, you have, and as computer scientists, I feel like you kind of know this, like we can only control things, like we can really only, like as far as real world goes, like the continuity, like we don't have like infinite precision over things, right? Like really we can kind of only control things up to a certain discretized point. And so that's where I was kind of getting that application, but seeing what Max was telling me about like the applications of hybrid systems to other applications was really fascinating. And I didn't actually know about all of that. So that was really cool.
Sean, Brennan, et cetera, if any of you have questions, you should jump in. Otherwise, I'll keep asking because I've got plenty. Yeah, I guess the self-referential stuff is interesting to me. You said something else really interesting about noise, which maybe we could follow up on. So I guess like noise could also be used as a way to deal with you not knowing enough about the thing you're modeling, right? Like if you
Exactly.
only know how to approximate it to say, you know, the third order polynomial or something like
Right,
this,
right.
then maybe you just kind of add some noise on the order of magnitude of the rest of the function. And then like in our context, a lot of what we do, I don't do this work, but people in my field do this thing where you'll have some polyhedra based tool that can put a bound on the behaviors of a hybrid system. And then you're like, I never want any state to be within this compact set. And that set might be something like the nuclear reactor is too hot or something. And then like you use the tool with some elaborate model that a grad student spends months writing, and you like prove that it's not going to be in that set because the tool over approximates the behavior and that polyhedra doesn't intersect, right? And so a lot of times when you write those models, you are kind of approximating many different, much more complicated things. Like you don't really know what differential equations fully characterize the flow of water in a vat or something. But I guess if you use noise, you could kind of deal with that, right? Because you could have noise on the order.
So this is one thing that I mention a lot when I kind of give that talk about like inputting, you know, perturbing a system with noise is, again, when I'm working with a real world system, like we don't have infinite precision, right? I can't guarantee that I'm going to, like something is going to happen and there's going to be no error on that, right? There's just no way. And so like, it makes total sense to introduce like an error term, you know, that's on the order of epsilon that allows you for some wiggle room in these parameters. And by adding that, you know, by saying like, oh, I only going to know something within plus or minus epsilon, that change, like I said, that changes up the dynamics like completely, right? Like I said, you can take an previously unstable system and make it stable. Just by adding in that little bit of noise there. And so this is something that I'm kind of like, I guess, again, I mostly talk to theorists, but if I were to talk to people who apply this stuff, I might encourage you to think about like, where is there room for error and how does whatever you're doing change if you include error in your model? Right? Because you might think that like, oh, this little wiggle room isn't going to matter that much. Like it could. And so I guess my advice to you all is in whatever you're doing is to think about that, right? Going forward is like, oh yeah, I've got this parameter here, but like really like this is only an estimate and I might have some plus or minus and be like, oh, okay, that's good enough. I'm just going to call it this. But like once you throw in, you know, some kind of like a residual or something on that system, is it going to change up the dynamics? How is it going to like, what are the ramifications down the road for how this is going to change up? And so that's something I kind of encourage people to do.
Yeah, in formal methods, we have like safety properties and liveness properties. And liveness properties are these ones that are disproved by an infinite trace, whereas a safety property can be disproved by a finite trace. And a lot of times in my experience with security systems or like systems where there's security properties that you want to preserve, you'll do this thing where you say, imagine that the adversary can make some changes to the system, like some list of changes. And then you ask, are these properties that were preserved, are they still preserved? And often when the liveness properties are violated, it's because there's a steady state that was unreachable in the original system, but is reachable in the perturbed one, which is exactly what you're saying, right?
That's
it's not
exactly
noise. Like in the discrete case, I wouldn't consider it noise exactly, but it's the same. It's the same basic idea.
Yeah. No, that's exactly it, right? Is like once you add in that little bit of wiggle room, like you've reached these unreachable states, because all these things do kind of add up and compound as you go down the road. They don't like kind of sit in this isolated system.
So you introduced this metric, and something that I would give as like a criticism of a lot of math papers that relate to FM topics that I work on is that they'll often introduce metrics that I can't actually calculate with a computer. Like there's this paper I really like from some people at ETH Zurich, where they introduced a metric on linear temporal logic formula to figure out how different two formula were, but it was like, you couldn't compute it. It was like an infinite number of, steps to compute. So I'm like, what's the point? Like I try to compute things here. So can you tell us a bit about your metric? Is it, can I compute it? Can I approximate it? And maybe more intuitively, like, does it tell me something intuitive that's useful, or is it more like it's mathematically useful as a gadget in order to allow us to use a bunch of other theorems or something like
that? Okay, so whether I compute it with a computer, I would say yes. Again, I'm totally a theorist, but like really, like this integral here is sort of scary looking, but really all you're doing is you're measuring, like if I have two functions, I'm just going to split up the functions into like unit intervals, right? So the interval from 0 to 1, the interval from 1 to 2, the interval from 2 to 3. And then on each of those intervals, I guess it does kind of require you to do like infinitely many of those.
I can ignore stuff that's far away, right? Because
sure, you could ignore stuff. I mean, that's going to kind of get us into like that estimation error thing, right? But like, sure, yeah, you could, if you needed something only up to a certain precision, right? You could only do a finite number of these. But like on each of those intervals, all you're doing is you're just measuring like, okay, on this interval, do the two functions agree ever? Or like, and how much do they agree and how much do they disagree? And since these functions are piecewise constant, you're not going to see something like this where they only agree on like a point, right? They're going to agree on like a significant overlap, right? If they agree, or maybe they don't, or they don't. So all you're doing is you're just kind of adding up all of the little lengths of where do these things agree, where do they disagree, and because they're piecewise constant, you get like a positive measure, right? You're not going to see two functions kind of
right.
This.
So it's like the Lebesgue measure of the and of the two functions.
That's exactly what it is. That's exactly, okay. Yeah. That's exactly what it is. And again, you do kind of weight it so that stuff in the middle is more important than stuff way out in the tails. So I guess you could tell me whether you can do that on a computer. I believe you can, aside from the whole fact that you have to do this infinitely many times. But like you said, like you mentioned, if you only needed up to a certain precision, right, you could cap where you do this sum. So I believe you can do that on a computer.
yeah, definitely.
So yeah, it's actually, this space here is very, very cool. I started by studying this as a completed discrete, like a sequence space. And the dynamics on that are really fascinating because it's not like we're used to thinking about, as human beings, we're used to thinking about things like in Rn, right? In like Euclidean space. But this space, it's a metric space, but like topologically speaking, the topology is like super, super weird. For instance, like if I have a ball, like if we're thinking about balls in Rn, like there's only one point that's going to be in the center, right? There's one point in the center and then everything's else. But in this metric space, if I have a ball, any of the points can be considered the center of the ball. They all kind of are like, it's you can't picture it because it's not Euclidean, like it's super weird, but it's like the way that they are in reference to each other is like any one of the points that's in the ball you could rewrite it such that that was the center of the ball. And so I think it's fascinating, and it kind of gives you this like super weird topology that is still metrizable. So it's an example of like weird spaces out there that are not Euclidean. So
that's super cool.
Yeah.
Can you tell us a little bit about your current research? Like what do you think are kind of interesting, exciting things of hybrid systems that you're working on or want to work on?
So I mentioned right now I'm doing the kind of like stochastic perturbation stuff, right? So like if I don't know exactly what the switches are going to happen, but maybe I can have some sort of a probability distribution. Like maybe I have like a Poisson distribution that tells me like when the switches are going to happen, right? That is introducing that randomness to the system, whereas I don't know things exactly ahead of time. And like I mentioned, like introducing that noise, that randomness can shake up the whole dynamics of whatever you're studying. That's kind of the one major hybrid systems project that I've got going on right now. I am also doing, this is like completely different. I'm working with a biologist friend reached out to me, and he is studying genomic data. And I don't know anything about genomics or genetics, or I've had to learn a lot, but I was looking at, he was like sending me all of this genetic data, and it's basically just like big long sequences, right? Like it's just sequences of AGs, Cs, and Ts. I think those are the right ones. And my mind immediately leapt to like kind of these function spaces, like these switchings, right? I was like, oh, we have like a finite number of states that we kind of switch between. And so I kind of introduced basically this idea, this metric here into like how we want to, like, if I'm looking at this genomic data, how can we compare like two individuals or two like alleles of individuals, like how similar and how different they are by some kind of a weighted metric like this. So not totally hybrid systems related, but it did kind of borrow inspiration from this, because I was like, I'm exactly looking at this idea of like a finite number of spaces, and I'm kind of switching between. So I'm, we're still seeing kind of like the application of those ideas elsewhere.
That's cool. There's a professor who does sort of similar work named Kekia Noglu at the University of Arizona. He develops algorithms for processing genetics data. But I can email you his link offline. You might.
Please do. That sounds fascinating. Yeah, that would probably be helpful to look at.
We've taken very generously an hour of your time, so thank you so much. Sean, Brennan, Alex, Daniel, if any of you have a question, this is, speak now or forever hold your peace, because we should.
I mean, you can feel free to email me afterwards. Like, you do not have to hold your peace forever. But yeah, thank you. This has been a lot of fun chatting with you all. So thank you so much for having me and putting up with that petition for an hour.
This was terrific. We really appreciated your time. Is it okay if I post this online, or would you prefer if the video is just like internal to the?
You can post it online. That's fine.
Okay, sounds great. All right, thank you. This was a blast. We really appreciate your time.
All right, thanks so much, everyone.
Okay, bye.